So your unit exam on Thursday of next week will have 15, that's 15 multiple choice questions. All right. The multiple choice questions are asking some kind of basic recall stuff, and there are a couple of situational questions where you got to read a small box of text that tells you about a certain situation, okay? And then the multiple choice question would ask something about how Newton's first, second, or third law apply in that situation. Okay, so there's a couple of those, but for the most part, it's kind of basic knowledge and understanding kind of stuff in there, and some simple calculations. There are 6 problems in the written response. Okay, 2 of them have a part A and a part B. Right. I'll go over what kind of things will be in there in a minute, but that's your test. It should be a bit shorter than Unit 1. Okay, but if you're not prepared, it won't feel like it. Okay, if you are prepared, okay, you study, you've done all the stuff I've asked you to do in class, you're through all those worksheets that I gave you on Newton's second law, okay, done all the energy stuff, you won't see anything on that test you haven't done before. Okay, Thursday. All right, so first thing we went over in this unit was Newton's first law. Right, which we sum up in one word: inertia. The tendency of an object to continue doing what it is already doing in the absence of a net force. Okay, Newton's first law governs all situations in which there is no net force. Thus, in all Newton's first law situations, there is also no what? Acceleration. Okay. All right, so those are the big things we need to remember about Newton's first law. There's no math to do with Newton's first law. Okay, there's no problem solving to do with Newton's first law. We just have to understand what kind of situations it governs. Okay, it governs an object traveling at a constant velocity or an object at rest. Okay, either one of those situations would be the result of all forces having a vector sum of 0. Okay, then we spent the bulk of the unit talking about this. If there is one thing on this test worth significantly more points than anything else, it is Newton's second law. Okay, I would say that on this test of the, what is it out of, I want to say like 50 some marks. Anyway, okay, whatever it's out of, it's easily 2/3 of those marks are somehow related to, if not directly asking about, Newton's second law. Okay, so make sure you're well versed in that. Okay, you know what kinds of problems I really like, inclined planes. Okay, so you know what kinds of things I'm going to ask. Right, some of the questions are very straightforward. Okay, even the written response, some of them are very straightforward, not mathematically difficult at all. Right, but you have to read them carefully. Okay? And like I said, there will not be a single question on that test that you have not done a problem like several times already. So make sure you're going through the worksheets. Okay, look at your Newton assignment when I give it back to you on Monday, stuff like that. Okay, expect to see similar things to what you saw on those sheets. Okay, so a lot of this is going to have to do with problem solving. Okay, and we have to remember, okay, that net force is mass times acceleration, and it is also the vector sum of all forces. Okay, and that is probably the trickier part of it. Okay, being able to draw that free body diagram that has all the forces on it so we don't miss anything. Okay, or doing the vector stuff, remembering, I got to find the horizontal component and the vertical component, okay, and all that kind of stuff. Okay, expect that there will probably be some Newton problems on the test that will involve you having to do some vector analysis. Okay, I mean, we've done a whole bunch like that. We did, signs that were hanging, those static questions, those involved vectors. Okay, inclined planes involve vectors. We did that question with the box on a flat surface. Okay, like you had one like this on your Newton assignment that you just handed in, right? That's a vector analysis question. It involves friction, which allows me to test more than one thing at a time, right? Know that I usually try and maximize my questions so I don't have to put so many on the test. Okay, so that means one question might be testing more than one thing. Okay, that question tests Newton's second law, vector analysis, friction is mu times Fn. It tests all of those. Okay, so in that way, it's a good question to use possibly on a test where you might have to show me all of that stuff. Okay. All right, so lots of applications of Newton's second law that we've gone over. Okay, another one to remember is the laws governing systems. Okay, remember that F net acts on all the mass. Okay, it acts on all mass, and as a result, all masses in a single system accelerate at the same rate. Okay, that was important when we did pulley questions. It was important on our Newton lab. Okay, it was important when we did some of those Newton's third law questions where you had 3 boxes in a row. Okay, and we had to recognize all of them have the same acceleration because they're part of a system. Okay. All right, so like I said, that's the biggest part of the test. Make sure you spend a significant amount of your studying time looking at Newton's second law examples. Okay. All right, after Newton's second law, we talked about Newton's third law. Okay, Newton's third law says that force 1 is equal to negative force 2. In other words, every action has an equal and opposite reaction. Okay, there is a written response problem to do with Newton's third law. Okay, like some of the multi-box system questions we did in that part of the unit. Okay, so would probably be a good idea to go over a couple of those. Okay, maybe watch the podcast where we did like 4 of them in one day, okay, so that you remember how they work. Right? That's all there is. There's not a lot on Newton's third law. There's like 1 written response problem and maybe like 2 multiple choice questions asking about Newton's third law. It's not something that's heavily weighted, but it's something you need to understand. Okay. Now remember that any problem solving to do with Newton's third law is done using Newton's second law. Okay, we use F equals ma, we use vector sum of all forces to solve, okay, Newton's third law problems. We just have to recognize that when box A pushes on box B pushes back on box A with an equal but opposite force. Okay, that's really all we need Newton's third law for. Then we go to vector sum of all forces to do our solution. Okay, it becomes a Newton's second law problem after that. Okay, after Newton's third law, okay, we talked about work energy theorem. Okay, so that means that work is a change in mechanical energy. Right? If a force is exerted through a distance, then work is being done. Okay, how many problems did we do where we actually had to use the cosine theta part? It wasn't many. Right? Most of the time, the force doing the work was in the same direction, okay, as the work being done. So just know that that part is there, but it's probably not going to be that important. Okay, you probably will have to do something like this. Okay, you'll have to solve a problem or 2, okay, that involve force times distance and some change in mechanical energy, either potential or kinetic or possibly both. Okay, we did do several questions where, you know, an object was pushed up a ramp or accelerated up a ramp, and we had to calculate something about the work done in that situation. Okay, so we've done a bunch of questions like that. Okay, worthwhile to probably go over those as well. Okay, and then lastly, well, not lastly, because there's one thing we haven't gone over yet. Okay, We did law of conservation of mechanical energy the other day. Okay, that's review of Science 10. How do you know if a problem is a law of conservation of energy problem or a work energy theorem problem? Like, how can you tell the difference? Because they give you a lot of the same information, right? They give you, a final velocity and an initial velocity. They might give you a final height and an initial height. They give you a lot of similar information. What will a work energy theorem problem give you that a law of conservation of energy question will never give you? Okay, if there's any mention in the question of energy changing, like mechanical energy changing, then it's not a law of conservation of energy problem. Because in a law of conservation of energy problem, energy 1 and energy 2 are the same, okay? Another thing that a law of conservation of energy question will never give you, okay, that a work energy theorem question will, is force, okay? There's no forces involved. Well, I mean, there are, but they're not important in a law of conservation of energy problem, okay? Because there's not going to be any change in work. There's no force times distance. The energy 1 and energy 2 are the same. Now, is it possible for me to ask a question that would have part A being a law of conservation of energy problem, like let's say, a toboggan goes down a hill, and then I have you figure out maybe how fast it's going at the bottom, and then part B can be a work energy theorem problem. Is it possible for me to do that? It could be. Right? Now I say at the bottom of the hill, they put on the brakes and you need to figure out how far they'll slide before they stop. Suddenly that's, okay, so now I solved a conservation of energy problem and then Coderre gave me a force in part 2 and I got to calculate how far they go. Okay, so it's possible for those two to go together. Okay, you just have to read them carefully to know which part is which. Okay, as soon as it gives you a force, okay, it's either Newton's second law or it's work energy theorem. Okay, if it doesn't, if it says, this thing is just going down a frictionless hill or they jump out of a plane, it's just gravity acting, then it's a conservation of energy question. Okay. All right, so just understand there will be some EI equals EF stuff in the written response, and there's a couple of multiple choice questions about it as well.
When we have to use the answer of part A and part B, do we use the rounded value?
Yes. Okay, so that's a good question, guys. If I've done part A and I've come up with my answer with the right number of significant figures, if I have to use that answer in part B, do I use the rounded value or do I keep all the decimals? The answer is you use the rounded value. Okay, that number was a separate calculation. You have to apply significant figures to it before using it anywhere else. Okay, it's not the same as if I'm doing one question that has multiple parts, okay, like not A, B, and C, but I have to do a whole bunch of calculations to arrive at a single answer, then I carry my decimals all the way through. But if a question is A, then B, okay, B has to start with significant figures. Okay, don't carry all the decimals over. Part B starts with the significant figures from part A. Okay, so that, yeah, good question. All right. Also, thing to remember, constants from the formula sheet do not count towards significant figures. All right, so if I've got, let's say, a question where they give me, I don't know, like a bunch of, like, let's say a mass and it's like 4.572 kilograms, and then they give me VI is 242.57 meters per second and something like that, and I have to use gravity. Okay, well, gravity on your sheet looks like that. Okay, but whatever answer I calculate will have 4 significant figures. This 9.81 is constant. Okay, it is given to you on your formula sheet. You treat it as an exact number. Okay, so any constants you take off of your formula sheet do not influence your significant figures. Okay, it's pretty rare where that ever happens. I usually try to avoid that happening at all. Okay, I don't think it should be a factor on the test. I'm trying to think if it would be, but I don't think it will. Okay. And then the one thing we haven't gone over yet that we will go over next week is power. Okay, we haven't gone over power yet. It's very straightforward. You won't have to do any calculations to do with power. You just have to know what it is. Okay, so we'll on Wednesday, I'll teach you power. Takes about 10 minutes. Okay, then we'll do a little activity to do with power. Okay, that'll have like more calculating to do with power than the test will, and that's it. Okay, basically you just have to understand that power is the rate at which work is done. Okay, power talks about how fast you get work done. Okay, so if I have a 20 horsepower snowblower and a 10 horsepower snowblower, which one will clean my driveway faster? Yeah, the 20. Will they both clean my driveway? Yes, they can both do the same amount of work, but the 20 horsepower snowblower is more powerful. It'll do the work faster. Okay, that's all work. That's all power is. That's all you need to know about power. Okay, is how fast work gets done. I'm not going to make you calculate anything about it. Just understand that a power rating, and in the metric system, obviously we don't use horsepower. In the metric system, we use watts. Okay, watts are the metric unit of power. A watt is a joule per second. Okay, so a 60-watt light bulb uses 60 joules of energy per second. Okay. It is a lot, actually. That's why we don't use incandescent light bulbs very much anymore, right? They're not very efficient. Okay, we can replace a 60-watt incandescent bulb with like a 4-watt LED. Okay, it's way more efficient, right? Okay, so that's all you'll need to know about power, but I'll go over that again on Wednesday. Okay, that's it. That's what's on there. Okay, so the bulk of it is Newton's second law. So make sure you go over as many examples of Newton's second law as you can. Okay, look at the problems I put in the review package. Okay, but even more than that, look at the problems that are on your worksheets. If there are any worksheets you haven't finished on Newton's second law, I would suggest finishing them as part of your studying. Okay, especially since on those sheets you have the answers, right? You can check back and see if you've done them right. Okay, and you still have next week, okay, Monday, Tuesday, and Wednesday, where you can come in and ask me for help. Okay, so if you've gone over stuff on the weekend and there's something you don't get, then come in and see me. Okay, come in, see me in scheduled help. Come in, see me at lunch. Okay, I'm going to be here, so come in and ask for help if you need it. All right. Okay. Are there any questions about anything that's going to be on there? How much is the whole test out of? The whole test is out of 59 marks. So there's 44 marks in the written and 15 obviously in the multiple choice. Okay, I think your kinematics test was out of 60 something, so okay, it's a bit shorter. Okay. All right, other questions? Okay, anything you'd like me to review in more detail? Systems? Okay. All right, so again, the big thing about any system is that the net force is acting on all of the mass. Okay, so if we're looking at like a, series of boxes, okay, if they tell me that the acceleration of the system is 1.2 meters per second squared, that means that box A's acceleration is that, box B's acceleration is that, box C's acceleration is that. Okay, that's what we have to remember about systems. From there, I can break up the system if I want to. Okay, I can figure out the forces on individual parts of the system. I can find the net force on individual parts of the system because I know what their accelerations are. Okay, and usually that's what we ended up doing. Okay, if we were trying to figure out the force of C on B, okay, we would say, all right, so here's box C. It's being pushed forward by a certain amount of force. It's being, okay, and in this case, there was no force acting backwards on it because let's say it was frictionless surface. Okay, well, I could figure out the net force on C, and that would be this force because there's only one force pushing on it, box B, right? And then it would push back on box B with that same force. Okay, so the big thing about systems is, remember, if you're given their acceleration, the acceleration of the system, you know the acceleration of all parts, and that can help you find the net force on each individual apart. Okay, and then you can treat it as a Newton's second law problem from there. Okay, all right, there's this force on box C, there's this force on box C, there's that force, and you can do a sum of all forces thing. That's how all systems will work. Okay, so the big thing is, remember, they all accelerate at the same rate. Okay, or if you're given the acceleration and asked to find the mass of one part, okay, remember that the mass you calculate is going to be the mass of the system. Okay, you'll have to subtract. Yes, it would be one of the forces acting on box B. So if this is a frictionless surface and I'm drawing the free body diagram for box B, okay, there would be the force of A pushing B, and there would be the force of C back on B, right? And if there was friction, then friction would be in there too. Okay, yeah, right. There isn't, but like the fact that C pushes back on B doesn't affect C in any way. All right, what else? Okay. The period comes after the T. Sorry, it takes quite a long time to think up a question like that. Okay, so essentially what I have is this situation. Okay, here's the St. Lawrence Seaway. Okay, here's the boat. Okay, but it's being pulled by something that's on the shore. Right, so the boat's moving this way, but the force is this way. Right, the angle between the direction the boat goes and the direction the force is pulling is 30 degrees. Right? So in this case, knowing that this force is 10,000 newtons, okay, I am only needing to know this part of the force because that's the part of it that's doing work. The boat isn't moving this way. It's not moving downwards on my diagram. Okay, it's just moving along the St. Lawrence Seaway. That's where I would use work equals F cos of theta times D. So I take my 10,000, multiply by the cos of 30 degrees, and multiply by 4,000 meters. That would be the trick on that question. Okay, 4,000 meters, and then I would have my work. Okay. Yep. No, I'm not going to bring in anything like projectile motion on the test. No. Okay. It'll be stuff that you've done regularly on a worksheet or things like that. Okay. What else, guys? An elevator one? Yep. Okay, so typical elevator question. Listening, please. Okay, typical elevator question. I'm told that the mass of the elevator is 300 kilograms, okay, and that it is accelerating downwards at 1.5 meters per second squared. All right, so the two forces that would act on an elevator would be the force of gravity and the tension in the cable supporting the elevator. All right, what things can I calculate right now? I can calculate FG, okay, so I'm going to go 300 times 9.81. All right, so FG is 2,943 newtons. What else can I calculate? Fnet, right? I can calculate Fnet because I know, okay, that the acceleration is 1.5 and the mass is 300, okay, so that's going to be 450 newtons down. Okay, so I know Fnet. I know there's two forces contributing to it. I can find the missing force using now the vector sum of all forces. Tension plus the force of gravity. Okay, so I'll have Fnet minus the force of gravity equals tension. Okay, so that'll be 2,943 minus, sorry, not 200, sorry, 400, negative 450 minus negative 2,943. Okay, and that would give me my tension in the cable. All right. Why didn't that come in at the beginning of class? I would have handed it in because it costs you 30% now.